Now let me walk you through a real example of populating an AVL tree so you understand how exactly they balance themselves. Here we have an empty tree. We want to insert 30 in this tree. We simply insert it in the root. Our tree is balanced, no problem. Next, we want to add 15. 15 is smaller than 30, so it should go on the left. Our tree is still balanced. Now we want to add 18. 18 is smaller than 30 and greater than 15, so it should end up here. Our tree is unbalanced. Here's the proof. We start with the node that we just added. We calculate the height of the left and right subtrees. At the 18, we don't have any children, so on both sides, we have a height of 0. For the 15, we have a height of 0 on the left and a height of 1 on the right because we have one edge on the right side of 15. And for 30, we have a height of 2 on the left and a height of 0 on the right. So our tree is unbalanced. The imbalance is in the left child, right subtree. So here we need to do a left-right rotation. We should rotate 15 to the left, so we put a weight on top of it, it drops, and 18 goes up. Now we have a left skewed tree, so we should rotate 30 to the right. This is going to bring 30 down and move 18 up. Now our tree is perfectly balanced. Let's add another number. We're going to add 10. 10 is smaller than 18 and 15, so it should end up here. Is this tree balanced? Let's find out. For the 10, we have a height of 0 on both sides. For the 15, we have a height of 1 on the left and a height of 0 on the right. And for the 18, we have a height of 2 on the left and a height of 1 on the right. The difference is still 1, so our tree is still balanced. Next, we're going to add 16. Our tree is still balanced. But what if we add 7? 7 is smaller than 18, 15, and 10, so it should end up here. Now our tree looks unbalanced, but let's prove it. We start with the node that we just added. At this node, we have a height of 0 on both sides. For the 10, we have a height of 1 on the left and a height of 0 on the right. For the 15, we have a height of 2 on the left and a height of 1 on the right. And for the 18, we have a height of 3 on the left because this is the longest path, and we have a height of 1 on the right. The difference is 2, so our tree is unbalanced. The imbalance is in the left child, left subtree. So we should do a right rotation. But this one is slightly tricky. We should rotate 18 to the right because this is where we have unbalance. However, when we rotate the 18 to the right, the 15 is going to go up and the 18 is going to come down and become the right child of the 15. So before we perform the rotation, we should temporarily disconnect 16 from the 15 and bring it down to create some space. Now we perform the right rotation. This is going to bring 18 down and make it the right child of the 15. Now we should attach the 16 somewhere. But where? Well, 16 is greater than 15 and smaller than 18. So it's going to become the left child of the 18. Now our tree is balanced again. So let's add one more number. Let's add 8. 8 is smaller than 15 and 10, but greater than 7, so it should end up here. Now let's calculate the heights. For the 8, we have a height of 0 on both sides. For the 7, we have a height of 0 on the left and a height of 1 on the right. For the 10, we have a height of 2 on the left and a height of 0 on the right. So our tree is unbalanced, and the imbalance is in the left child, right subtree. So we should perform a left-right rotation. So we want to rotate 7 to the left. This is going to bring 7 down and move 8 up. All right. Now we should perform a right rotation on 10. 10 is going to come down and 8 is going to go up. And our tree is going to get balanced again. So this is how AVL trees work.